So I'd now like to introduce Michael Penston Thesis Prize winner, Dr. Sownak Bose from Harvard Smithsonian Center for Astrophysics, who's going to talk on cosmology beyond cold dark matter. Sownak.
Thank you. I like to establish where my allegiances are right in the beginning. Okay. So I should probably start with a sort of administrative point, which is that the Harvard-Smithsonian Center for Astrophysics has undergone a pretty radical rebranding, and it's now called the Center for Astrophysics, Harvard and Smithsonian. I only wish that they would have corrected the way they've spelled center in the process, but alas, they couldn't get that through. So it's my pleasure to give this talk today, and what I wanted to do was to tell you a little bit about some of the things that we've come to learn over the past few years about the nature of dark matter, and specifically about candidates of dark matter that go beyond our standard cosmological paradigm. And the sort of line of investigation that I want to take is to ask this particular question, which is how can numerical simulations or computer programs of structure formation actually inform us about the nature of dark matter being something that is sort of, by definition, something one cannot observe. We have to use theoretical tools to do so, to at least learn something about it. And the starting point that I want to take is to actually establish what the standard paradigm is and why it became this way. And so cold dark matter, which makes up about 25% or 30% of the energy density of the universe, has become, by the way, I should say it's called cold in a sort of kinematic sense, that the particles have almost no thermal velocities to them, and so they're sort of kinematically cold. And they really have become the standard paradigm for our understanding of dark matter, primarily because it is very successful at explaining a very wide range of phenomena across a wide range of scales, both temporal and spatial. So the same model that can be used to fit so beautifully the sort of temperature fluctuations measured by the cosmic microwave background using the Planck satellite is also the model that can be then used through numerical simulations to find a very nice agreement in the actual large-scale distribution of galaxies. So that's sort of shown in this figure on the bottom right, where the wedges at the top and on the left show the distribution of galaxies that have been observed in galaxy redshift surveys, underlying and showing the sort of beautiful sort of cosmic webbed type distribution of galaxies. And on the wedges on the right and at the bottom, these are actually predictions from numerical simulations of what the distribution of galaxies should look like if cold dark matter is the correct description. But it's actually worth a historical aside to try and find out where the sort of interest in particle dark matter actually came about in the first place. And from what I can tell, it actually comes about as a sort of experimental accident in this particular paper that was just published by physicists in the Soviet Union in the 1980s, who claim to have measured the mass of the electron neutrino from the endpoint decay of tritium. And in this paper, they claim that the mass of the neutrino was somewhere between 14 and 50 electron volts. It turned out to be wrong by a few orders of magnitude. But this was very exciting for astronomers, at least at the time, or cosmologists at the time, because this is roughly the sort of mass range that a neutrino would need to have in order to be able to actually provide all of the relic abundance of dark matter. And so this is where the particle interpretation of dark matter became a really big thing, even though the result was later shown to be incorrect. And the neutrino actually ticks a lot of useful boxes when it comes to being a sort of dark matter candidate, being that A, it's useful that it's a particle that we actually know about. It's a particle that is not visible, hence the dark side of it, I suppose. And thirdly, the interactions are very weak, so they're quite difficult to actually detect and measure. And a sort of very defining characteristic of neutrinos is that these particles, owing to their very, very low rest masses, zip around the universe at very nearly the speed of light. And this velocity essentially acts as almost as a pressure that counteracts the effect of gravity on very small scales and prevents the very tiny structures from forming. And this will actually have a pretty significant effect on what the universe actually looks like if these kinds of particles were the dark matter. So because of this velocity nature of it, these are candidates called hot dark matter. So when it comes to simulating dark matter, there's a fairly well-defined set of steps that one needs to follow. So you assume a particle theory for dark matter, and you generate a set of initial conditions according to this particle theory. And of course, we know how much dark matter there should be based on observations of the cosmic microwave background and measurements from the cosmic microwave background. You then evolve the simulation box according to the laws of gravity, which are fairly well established through laws of Newton and Einstein. And you then compare your results of the simulation with observations to see how well you've done. And then the last step is possibly optional. And so this is what people did in the 1980s. And they constructed these simulated universes of hot dark matter dominated by neutrinos. And essentially what they found was that it gave you a complete garbage. So in the sense that the resulting universe looked absolutely nothing like what the actual observed universe was like. And so the authors here mention that the coherence length of the neutrino distribution is very, very much larger than what was actually observed for the clustering of galaxies in the real universe. So what does that actually mean? So here are a couple of visualizations of these hot dark matter universes. There's a paper from 1983 by Klippen and Shandaran with 32 cubed particles, the state of the art at the time. And you can see the two panels at the top show what the distribution of galaxies would look like in a neutrino-dominated universe compared with what was then known as the distribution of galaxies at the bottom. And you can see that they look absolutely nothing alike. So you see a lot of small-scale clustering in the observed universe, which is completely absent in the neutrino case, where you see these very sort of dense knots connected by filaments that are stretching around 60 megaparsecs across the universe, which had no counterparts in the observed distribution. And in fact, the authors went one step further, and they said, oh, let's try and visualize this in sort of 3D, and they sort of connected these points and formed isodensity contours to get an image that looks something like that. And so this paper has since then, in the community, been known as the chicken universe paper for reasons that should be pretty obvious. And so the step after this was very obvious, which is that you said, okay, well, hot dark matter doesn't work. Let's go to the kinematically opposite limit of cold dark matter. So rather than having particles that zip around near the speed of light, let's go for completely the opposite limit, where particles are more or less stationary. And so these two panels at the top again now compare. There's a paper by Davis, F. Statue, Frank, and White in 1985, again with 32 cubed particles. And you can see in the two CDM simulations, they just vary slightly in the cosmological parameters that are assumed. The distribution actually looks quite a bit like what the observed galaxy distribution looks like. In fact, in perusing this paper, you'll find that the best fit model turned out to be a universe in which dark matter makes up about 30%, and 70% is attributed to something called a cosmological constant, which is interesting because it's about 14 years before the accelerated universe observations were made, but no one actually gave any credence to the cosmological constant model because people believed in the omega matter equals 1 type universe in those days. Now, fast forwarding 20 years, if we've learned nothing else, we've at least managed to produce far better images of simulations. And so this is the pioneering work of the Millennium simulation performed in 2005. And this is now showing a cold dark matter universe with almost 10 billion particles in it. And you can actually see this wonderful sort of cosmic web type imagery shown here with dark matter halos shown everywhere and galaxies which would eventually reside within the centers of these halos. And in looking at this picture, you can't help but sort of recall what the neurons in the brain cell looks like. And people have tried to make some sort of weird quantum consciousness and cosmology type links with this, which is not something I'll get into any detail. But essentially, the picture that we've come into and sort of formed is the following, that every galaxy in the universe is made up of stars and gas, and that's what those sort of things that look like fried eggs are supposed to represent. And each galaxy is surrounded by a halo of dark matter, which is roughly spherical for simplicity, I suppose. And big galaxies, like the Milky Way, are surrounded by tiny satellite galaxies, which themselves have their own dark matter halos. Okay, so, this is all great. We've had a description of dark matter which performs a very good statistical distribution of the large-scale structure. But then you can ask the question, what if the dark matter isn't cold? It isn't CDM. And you may ask, why would you want to do this, given the beautiful agreement on very large scales? Well, you can go to the very opposite end of the scale, and you can start looking at nonlinear structures. So this is one of the great triumphs of the dark matter paradigm, which is that it is predictive in nature. So not only can you predict large-scale structure where things are more or less linear, but you can actually form non-linear structures like Milky Way galaxies. So this is from the Aquarius project, which shows a visualization of the dark matter halo of the Milky Way predicted by the cold dark matter model. And you can see there's hundreds of thousands of tiny lumps of dark matter which would each host a satellite galaxy. And when focusing on these scales of dwarf galaxies and satellites, people have started to claim a few so-called problems of the CDM model. The primary ones here being listed as the missing satellites problem, which basically says that simulations of the cold dark matter model predict far too many of these tiny lumps compared to the actual number of satellites we have actually observed around the Milky Way, which are only around 50 or 55 or so. And the next two, which are essentially restatements of the same problem, the too big to fail and the cause versus cusps problem, which essentially says that the central densities of the halos that galaxies live in that one infers from observations seem to be far less dense than the centers of halos predicted by the cold dark matter model. And so the question is this the way we want to sort of motivate alternatives to the cold dark matter paradigm? And my answer to this is a very resounding no. And the reason for this is that all of these claims have essentially been made by comparing observations with simulations of just dark matter. Okay? So this is basically comparing apples with horses, and it doesn't quite work. And so in the past 5 to 10 years, what we found is that once you actually start modeling the influence of baryons and the interplay between the visible matter and the dark matter, a number of these problems actually go away. And so I don't think this is the appropriate way to motivate models. And I think the best motivation is simply the fact that despite a lot of money being invested in trying to detect the dark matter particle, we haven't actually found the dark matter itself. And so while this remains the case, it's always worth considering what alternatives there exist. And so if you were to do this, what can you actually how much freedom do you actually have to play around with the nature of dark matter? So this is a compilation of a variety of data sets ranging from very large scales to very small scales, and measuring the power spectrum, or roughly how clumpy the universe is on a particular scale, showing data from the cosmic microwave background, the very larger scales, to the Lyman alpha forest on the smaller scales. And the solid line in the background shows predictions of the cold dark matter model from linear theory, which at least visually seems to go through the points quite nicely. So what that means is if we are to play around with the nature of dark matter, the only leeway we really have is on very, very small scales, which is on the scale of dwarf galaxies. Okay, so in that respect, what I want to focus on is this particular example of sterile neutrinos as a sort of particular alternative, which is an example of warm dark matter, which, as you may guess, bridges the sort of hot dark matter and cold dark matter paradigm and tries to sort of bring in the successes of cold dark matter on the very large scales, but produces some sort of observably different phenomenon on smaller scales, which are not quite as drastic as in the hot dark matter case. Otherwise, they would have been ruled out already. And these particles have masses of the order of a few kilo-electron volts. And this sterile neutrino model received something of an impetus, coincidentally around the time when I started working on this problem a few years ago, when there were two independent groups who claimed to have measured this sort of mysterious excess of energy at the energy range of 3.5 kilo-electron volts in the spectrum of galaxy clusters and dwarf galaxies, which at the time they were unable to sort of attribute to any sort of known emission lines of atoms or some other astrophysical effect. And in fact, they said that, well, what this could be, this 3.5 keV emission, could be due to the decay of a sterile neutrino dark matter with a mass of around 7 kilo-electron volts. Okay? And one really and I should say, by the way, that this particular interpretation has undergone a lot of sort of back and forth in terms of criticism and support in the literature. Well, this is just a sort of anchor point in the parameter space that I want to consider. What's particularly exciting about this model is that it's not just the mass of the dark matter particle that goes into determining how different it is from cold dark matter. So this is a figure now that again shows this power spectrum that I was talking about before, but in the very, very early universe, before the first structures have actually formed. And the white curve there shows the case of cold dark matter, where you see that there's essentially some level of power or clumping on all scales from large to small scales. And the three curves that essentially peel off from the white curve are three variants of this 7 kV model with a slightly different particle physics parameter. Okay? And so in all cases, you see that on the large scales, they're identical to cold dark matter, and then they drop off, meaning that there's an absence of power. And this is essentially what we want to try and probe through simulations to provide some observable predictions. So you can make the dark matter essentially look more or less warm depending on the particular choice of particle physics parameters. Now, irrespective of which one you choose, the generic behavior can kind of be summarized in this one figure here. So what I'm showing here is the present-day mass of dark matter halos predicted to exist in each of these cosmologies, sort of plotted against the epoch or the redshift at which these halos formed, or you can think of these as when these galaxies formed as well. And so the cold dark matter case is shown in this yellow curve, and this sort of shows what is known as the hierarchical picture of structure formation, in which the very smallest objects are the ones that form first, and the very most massive ones form eventually through gradual merging and accretion of mass. And you see in the warm dark matter case, this is exactly the same in the very high mass scale of things, but then there's a sort of characteristic scale below which the trend reverses, and in fact, these halos form later compared to the cold dark matter counterparts. Okay, so the formation of halos below a characteristic scale is delayed. And all the differences that exist between these two models can be explained by this particular feature. And so as a summary of what actually happens, you have a delay of structure formation, you have an abundance of structures being suppressed, and the dark matter halos become less dense in the center as well. So what does this actually look like? So here is a simulation that shows what the dark matter halo of the Milky Way would look like in the cold dark matter case and in a rather exaggerated warm dark matter model. So you can see that the most massive structure, the Milky Way itself, is still sort of preserved, so good. We haven't actually wiped ourselves out in the process. But the difference really lies in the absence of these really tiny lumps, which are the satellite galaxies. Okay, so the question is, it should be pretty easy to tell whether we live in that universe or this universe. Okay, we can just go out and count the number of satellites. Unfortunately, it never turns out to be that simple, because it's not just the mass of the dark matter particle that goes into determining how many of these satellite galaxies there are, but in fact what one assumes to be how heavy the Milky Way itself is that actually has a big role in things. So this is an exercise that was performed quite beautifully by Rachel Kennedy, a former PhD student in Durham, who essentially plotted the mass of the dark matter particle on the x-axis and the assumed mass of the Milky Way on the y-axis, and basically tried to constrain these properties based on the observed number of satellites. And what she found is that obviously, if you have a very, very low mass dark matter particle, you would wipe out a lot of structure, but you can kind of match up with constraints if you assume the halo's mass to be quite big, and vice versa. So there's a big degeneracy when it comes here. And in fact, this is not the only degeneracy, but in fact, the way you actually model the astrophysical behavior of gas and star formation and so on actually has a big role to play in this. So rather contrary to what Amelie was saying in her talk, for me, the dark matter is a friendly component, and the astrophysics actually becomes the nuisance in actually constraining the dark matter. So I'm not really a big fan of counting objects, so to speak. So let's think about what I said before. So these halos are formed later on in a sterile neutrino universe than they are in cold dark matter. So presumably, if you look really far back into the past, we should be able to find a scenario, or at least an epoch, where these differences are exaggerated. So this is what I'm trying to show in this figure here. So this is again now showing the mass of dark matter halos. And the y-axis is essentially the number density of these objects per cubic megaparsec in these cosmologies. So the solid curves are showing the cold dark matter case, and the dashed curves are for this warm dark matter model, where you can see that, again, on very small scales, the abundance is suppressed compared to cold dark matter. And if you look at a very high redshift curve, say this cyan curve right at the bottom at redshift 10, you see that at the scale of around 10 to the 8 solar masses, there are about 5 times as many dark matter halos predicted in the cold dark matter universe than there are in the sterile neutrino case. Now, all of these halos are actually hosts of galaxies. So at these very high redshifts, presumably, if these galaxies are absent, there must be some effect on high redshift galaxy formation associated phenomenon that one can try and measure. Now, one very prominent example that we are aware of is something called cosmic reionization, which is the process by which the universe emerges from the period of the so-called dark ages, due to the formation of the first stars and galaxies, which end up ionizing the neutral hydrogen and, well, reionizing the universe in the process. So if the low mass halos are completely absent, or very, very low in abundance in the high redshift universe, does that mean that we are actually unable to reionize the universe in time in our sterile neutrino models, given the constraints that we have from satellites? And so this is sort of depicted in these two figures here. Now, again, with cold dark matter shown on the left, and a very, very extreme case of the 7 keV sterile neutrino on the right. So if any model were to fail, it would be this one. And so what's shown here is how many photons are produced by galaxies in each of these cosmologies per hydrogen atom that exists in the universe. And essentially, the universe in the simulated cosmology is ionized or reionized when the solid curve intersects with the horizontal dashed line. And the vertical bands that you see there are at least the constraints of the Planck satellite derived back in 2015. And you see that, well, the cold dark matter scenario has no problems in doing so. But curiously, in this extreme 7 keV case, despite the fact that the early generations of galaxies are completely wiped out, you know, it is maybe completing reionization a little too late, but in fact, you wouldn't say that it's statistically too off anyway. And that's quite interesting to try and figure out why this is happening. And the key to this is actually in looking at the slopes of these curves, which you see is far steeper in the model on the right. And so essentially what's happening in these cases is that despite the fact that the assembly of galaxies is delayed in the warm dark matter model, so this is showing the case of a particular stellar mass range of galaxies at a high redshift, at redshift 7, you see that in the cold dark matter case, the formation of stars begins far earlier and far later in the warm dark matter scenario. But once it does start, the curve itself is far steeper, showing that the buildup of mass itself is far more rapid in this case. And that's essentially, I can explain that, but probably run out of time to go into do much justice to it. And essentially, the galaxy formation is a very inefficient process, and the most inefficient ones are the really tiny objects, which are absent in warm dark matter, but present in cold dark matter. And the result is that the actual star formation rate at a fixed stellar mass is higher, and the result is that if you were to then use something like the James Webb Telescope to measure what is the abundance of galaxies at some given UV brightness at high redshift, you actually find the effect, which is contrary to naive expectation, in that it is actually the halos or the galaxies in the warm dark matter universe that end up being brighter in the UV, as opposed to, it's not actually more abundant, but rather brighter in the UV than their cold dark matter counterparts, simply because the galaxy formation process actually assembles very rapidly. But I'm not a big fan of counting objects, and I get very annoyed when all of this astrophysical stuff comes in. So let's go back to this picture. So again, this was really quite an obvious difference between the two, right? So the question is, can you actually directly measure the difference in the amount of dark substructures, rather than going into all the nitty-gritty of who formed which star? And so the question is, what do we do? How can we actually detect the dark substructures themselves directly, the gravity of it? And well, there is a very, very well-established technique called gravitational lensing, which helps us do exactly that. So in the realm of gravitational lensing, what we have is essentially a background galaxy and a foreground galaxy that acts as the lens. And as the light from the background galaxy approaches us in telescopes here on Earth, or wherever, the light bends around it due to the gravity of the foreground galaxy. And what you actually see as the image of the background galaxy is this sort of arc or an Einstein ring, essentially around the foreground. And the idea that we then want to do is imagine now if there was a tiny lump of dark substructure that were present in the foreground galaxy that then just passes by where this image has formed. You would expect there to be a slight perturbation to this image. You would expect a distortion to take place. So if there was no matter, if there was no lumpy stuff, you would expect a very smooth distribution of surface brightness around your lens. But if there was a big lump, you should see it as a big lump. And in fact, people have actually applied this methodology to observations and have managed to actually detect dark matter subhalos, or dark substructures, which are only a few tens of millions times the mass of the sun. And this provides a very, very powerful tool to actually measure the substructures themselves. And in fact, we showed that you could actually just collect a system of 100 strong lenses with the sort of present or future levels of detectability, and with very, very high significance, you can actually contrast the two models and clearly distinguish between the two. That's where I will leave you. Here are some of my final thoughts. I'll just leave it up there and let you read this in your own time. And well, thank you very much.
Thank you very much. Open for questions or comments. Yes.
A fascinating presentation, thank you. Just a suggestion, if by any chance dark matter is a product of one of the initial phase changes, is it possible that it's left cold if the other component or components carry away or are wholly or partly constituted of the latent energy of the phase change?
Yeah, so I mean, the particular example that I took here, which is of sterile neutrinos, are actually a relatively simple scenario where it's just a sort of primordial thermal velocity we're talking about. If I were granted maybe 10 minutes more, I would have gone into talking about something called interacting dark matter, where the particles at the time of their creation actually have some non-negligible interaction with the baryon plasma. And what this does is that it actually collisionally interacts with it and ends up showing oscillations in the power spectrum on very, very small scales. And these oscillations can, in fact, we've shown in simulations, be detected through not galaxy clustering, but through the Lyman alpha forest. And these possibilities are actually perfectly viable because they occur on scales that the cosmic microwave background doesn't actually probe. So they can be eminently present without actually ruining any of these sort of agreements on large scales that one requires. But it is certainly possible, yeah.
Richard.
Very nice talk. You said yourself that the cold dark matter has not been detected. There is another way of going, and that's fuzzy cold dark matter, where the particle is very, very low mass, has wave-like properties, seems to be getting a lot of attention.
That's right.
Should we put our money on fuzzy cold dark matter?
I mean, I am not a betting person to begin with, but I certainly think that it is certainly. And so the fuzzy dark matter model is actually, as you say, is something that I think in the past couple of years has really sort of accelerated in interest. And I think there's still a lot to be done in terms of how these models are sort of simulated. So the actual interaction of fuzzy dark matter with baryonic physics and galaxy formation physics is still quite in a nascent stage. And in fact, something that I'm working on with colleagues of mine in the US. But I certainly would say that it is worth keeping an open mind on all of these as long as there is a justified motivation for doing so, which is that there should be some element of realism to these models from the realm of particle physics for doing it. But yeah, that would be
One last question.
There also seems to be some very large objects very early on, supermassive quasars and so forth. Is this not a problem if it's warm dark matter to actually explain how such structures can form at high Z?
Well, I mean, I'm not sure how to really answer that because it's not obvious to me what the mechanism for forming these structures is. So, I mean, on the scale of individual stars, for example, you don't really expect there to be too much of a difference in actually what's happening. However, what would maybe change is when the first stars start forming, right? Which could then maybe say that, okay, if you want to form a very highly accreting quasar at redshift 8 or whatever, you might find it a challenge to do so in the warm dark matter model if it is delayed by too long, right? If the formation of the first stars and stuff is delayed by too much. I think that the models that are viable at the moment are ones that maybe sort of evade that level of things because the delay is only by maybe about a half a gigayear or so in terms of when the first stars are formed. But I certainly think that in order to address that question in greater detail, I think the actual challenge lies firstly in understanding what the formation mechanism of the first stars is, regarding what are the relevant channels of cooling gas and what allows these direct collapse black holes and these kind of things to actually form, which I think is very poorly understood regardless of what your dark matter model is.
Okay, thanks, Sownak again.